So in today's video, we'll be putting everything together to get a good picture of the graph. We'll use our first derivative to find intervals of increase and decrease and our maxes and mins. Then we'll use our second derivative to find our intervals of concavity. Then with each of those pieces of information, we will use it to draw a sketch of the graph. So to start out, we'll take our first derivative, which would be 3 minus 3x squared. And we'll go ahead and set this derivative equal to 0. And when we do that, we'll factor a bit. So we'll pull a 3 out, leaving us with 1 minus x squared. And the 1 minus x squared can factor into 1 minus x and 1 plus x. Remember, you only have to set parts that have an x equal to 0. So when you set 1 minus x equal to 0, you get x equals 1. And when you set 1 plus x equal to 0, you get x equals negative 1. Now, because this was a polynomial, there's no places where it will not exist. So our only critical numbers that we'll put on the number line are that 1 and negative 1. We'll pick values in each of our gaps to plug in our derivative. Remember, it's usually easiest to plug in the factored form. Let's take something like negative 10 million. Well, 1 minus a negative 10 million will become a plus, so that's positive. The 1 plus a negative 10 million will become a negative, so we'll have a positive in the 3 times a positive times a negative, which will give us a negative. When we put in something in the middle like 0, we'll have 3 times 1, which is a positive. And if you take like positive 10 million, you'll have 3 times a negative number times a positive number, which will be a negative. So therefore, our intervals of increase will be just from negative 1 to 1. From decrease will be negative infinity to negative 1. The union of that with 1 to infinity. We are going from decrease to increase, so we'll have a minimum at negative 1. We're going from increase to decrease at positive 1, so we'll have a maximum. So our min is going to be negative 1 comma something. Our max will be 1 comma something. Because those are points in our actual graph, we have to plug those into our original equation. So if we start with the negative 1, we know we'll have 2. Plug in the negative 1, you'll get back negative 3. Negative 1 cubed is a negative 1, so we'll have minus a negative 1. That minus a negative 1 will become a plus. So 2 minus 3 will give you negative 1. Negative 1 plus 1 is just 0. So our minimum, therefore, is negative 1 comma 0. If we do a similar thing with the positive 1 to plug in, we'll have 2. We'll have a positive 3, and we'll have minus a positive 1. So that'll be 5 minus 1, which will give us 4. So our maximum is 1 comma 4. We'll now take the second derivative. When taking the second derivative, it's probably going to be easier to do it with our original first derivative, not the factored form. Our second derivative will be negative 6x. We'll set that equal to 0, and we just get x is equal to 0. So we'll only have one value on our number line for that. When we plug in each of our gaps, remember we'll plug into that second derivative. When you take a number left of 0, that's negative, multiply it by negative 6, you get back a positive. When you take something to the right, a positive number, and multiply it by negative 6, you get a negative. So therefore, we are going to be concave up from negative infinity to 0, and we'll be concave down from 0 to infinity. Because we changed from concave up to concave down, and even if we had done the reverse of that, that means we have an inflection point. Our inflection point is going to be 0 comma something. This point is on the actual graph. Therefore, we have to plug it into the original equation. So we'll go back up and put in 0 for x. When we do that, we'll get 2 plus 0 plus 0, so that'll just be 2. So 0, 2, that means is an inflection point. We'll now use these pieces of information to sketch the graph. We had that 0, 2 was an inflection point. We had that our minimum was -1, 0. And our maximum was 1, 4. Now it's usually easiest to draw in the concave up and concave down parts and then check with your increasing, decreasing. So we need to be concave up from -infinity to 0, and we'll just have that minimum point being at -1. So we'll look something like that. And we need to be concave down from 0 to infinity. And we need to just have that point at 1 be our maximum, so we'll look something like that. Let's check our increase-decrease intervals out. We should be increasing from -1 to 1, which we are, and we should be decreasing -infinity to -1, and 1 to infinity, which we are as well. Our next example, for this one, if you want, and on your homework I'm okay with this, even though, and then when we're doing it in class, even though you won't be able to do it on the test, if you want to check at the very end with your graphing calculator, you can, just to confirm that you've gotten it correct. But keep in mind, you're not going to be able to do that on the test, so that's just a final last thing just to make sure you did it all the way correct. So we'll take our first derivative. We're going to do the same as what we did on the last one, which will give us 6x squared plus 6x minus 36. We'll set our derivative equal to 0. You can divide everything by 6, and we'll get x squared plus x minus 6. And that'll factor into x plus 3 and x minus 2. When you set those equal to 0, we'll get -3 and +2. Because it's a polynomial, there's nowhere that it won't exist. So -3 and 2 are our only values on the number line. We'll pick something in each of those gaps. And remember, it's usually easiest to plug into the factored form of your derivative. So take something like -10 million. You'll have a negative times a negative, which is a positive. 0 will give us 3 times -2, which is a negative. And +10 million will give you positive times a positive, which is a positive. Meaning our intervals of increase will go from -infinity to -3, the union of that with 2 to infinity. Our interval of decrease will go from -3 to 2. So we went increase to decrease at -3, so we'll have a max. Decrease to increase at +2, so we'll have a min. So our max will be -3 comma something. Our min will be 2 comma something. Because they're points in our actual graph, we have to plug them into our original. When we put in -3 in and cube it, it'll give you -27, times 2 will give you -54. -3 squared is 9. 9 times 3 is 27. And -3 times -36 will give you a positive 108. Combine those all together and you'll get a positive 81. When we take the positive 2, 2 cubed is 8, times 2 is 16. 2 squared is 4, times 3 is 12. And 2 times -36 will give you -72. -72 and 12 will give you -60. -60 and +16 will give you a -44. So we now have our max and our min values. And we'll move on to our second derivative. Now we've got to take it from here. So f double prime is equal to 12x plus 6. We'll set that equal to 0. We'll get negative 6 is equal to 12x, and x will be equal to negative 1/2. Again, it's linear. It'll be defined everywhere, so the negative 1/2 is our only value. Something to the left is like negative 10 million. When we plug it in here, we'll have negative 120 million plus 6, which is negative. Plug in something easy like 0, you'll get back a positive. So we are going to be concave down from negative infinity to negative 1/2, and concave up from negative 1/2 to infinity. Because we switched from concave up to concave down, and even if it was vice versa, that gives us an inflection point. That point is negative 1/2 comma something. Because it is a point in our actual graph, we've got to go to our original function. Negative 1/2 cubed will give us negative 1/8. Negative 1/8 times 2 is negative 2/8, which is really negative 1/4. Negative 1/2 squared is positive 1/4 times 3, which is positive 3/4. And negative 1/2 times negative 36 will give us a positive 18. Negative 1/4 and 3/4 gives you 2/4, which is 1/2. So this will end up equaling just 18.5. We'll now go ahead and sketch our graph. We've got negative 1/2 comma 18.5. We've got negative, and actually we'll bring this down a little further so we have room. So there's negative 1/2 comma positive 18.5. We have negative 3 comma 81. And we had positive 2 comma negative 44. So again, just drawing your concave up, concave down sections, making sure your maxes and mins are there, and then you'll use your increase, decrease to check. So we're concave down from negative infinity to negative 1/2, so we'll just look something like that. And then we're concave up the rest of the way, we'll look something like this. We should be increasing from negative infinity to 3, which we are, or negative 3, which we are, and from 2 to infinity, which we are, and decreasing in between there from negative 3 to 2, which is the case, so we are in good shape. Next example, a little bit trickier because we're going to work with a fraction. Same things we're going to find though. So we'll do our first derivative. Because we're dividing, we must do quotient rule. So we'll do low x squared minus 9, d high, which is 0, minus high, which is 1, d low, which is 2x, all over low, low. So the bottom squared. This will end up equaling negative 2x over x squared minus 9 squared. Now, because we have a fraction, there are some spots where it will be undefined. The bottom will be 0 if you put in a 3 or a negative 3 for x. So those will have to appear on our number line. Those are considered critical numbers. Now just keep in mind, we will not have maxes or mins there because those values actually won't exist, but that is where it could change from increasing to decreasing. And a fraction is made 0 when the numerator is 0. So when you have negative 2x equal to 0, that just gives you x equals 0. And that's our third critical number. We'll plug those into the derivative. Now, keep in mind the denominator is squared. When you square something, it'll always be positive. Therefore, that's not going to affect our sign at all. So we can just look at the numerator. Left of negative 3 will be a negative. A negative times negative 2 will be a positive. Between negative 3 and 0 will be a negative. A negative times negative 2 is a positive. And then the reverse, our other two sections will be positive. So when you multiply them by negative 2, they'll each be negative. So our intervals of increase will be negative infinity to negative 3. And the union of that with negative 3 to 0. Our intervals of decrease are 0 to 3. The union of that with 3 to infinity. Now keep in mind our function is not defined at 3 and negative 3, so you can't have maxes or mins there. And notice the sign didn't change anyway. The only spot we'll work with, we'll have an increase to a decrease at 0, meaning we'll have a max. That max will be 0 comma something, because it is a point in the regular graph. We need to plug it into the original equation. When you put 0 in for x in the denominator there, you'll just get negative 1/9. We'll go ahead and we'll take our second derivative. And we'll again do the quotient rule. So we'll do low times the derivative of high, so negative 2, minus high d low. So the derivative of the denominator, the 2 will come out front, x squared minus 9 now to the first. And we've got to do chain rule, so multiply by derivative of the inside, which you get 2x. This will all be over low, low. So we'll now have x squared minus 9 to the fourth. When you do a quotient rule, the second derivative, you will almost always find something that will cancel out. If something is going to cancel, it has to be in each term. A term is defined as a set of stuff that's being multiplied together. So this is considered a term, and this is all considered a term in our numerator. We would need something, if it's going to cancel out, to be in every term and also be in the denominator. Well, something that's in all those spots is an x squared minus 9. Each of them has at least 1. So we can take 1 x squared minus 9 away from everything. So this now becomes a 1. And this is now a 3. And now we can neaten it up. We have negative 2 is just distributing to the x squared minus 9, so that'll be negative 2x squared plus 18. We've got a 2x times a 2 times a negative 2x, and think of that negative as like a negative 1. So the 2x times a 2 will give you 4x. 4x times a negative 2x will give you negative 8x squared. And then times the negative will give you positive 8x squared. And that's all going to be over x squared minus 9 cubed. And we'll neaten that up on top. That's going to be 6x squared plus 18 all over x squared minus 9 cubed. So we need to note again that this second derivative will be undefined at negative 3 and 3. So that will go on our number line. Also, just keep in mind, like, you wouldn't have inflection points there because those points don't exist if they happen to change sign. And for this fraction to be 0, the numerator has to be 0. So we'll set 6x squared plus 18 equal to 0. Subtract the 18 over. And divide by 6, you get x squared is equal to negative 3. Well, when you take the square root, you get x is equal to plus and minus the square root of negative 3, which is imaginary. So in other words, there's no way to make the numerator 0. And if you think about it, it makes sense. When we need for this to be 0, that first term, the 6x squared, have to be negative 18. Well, when you square something, it's always positive, so that first term is always going to be positive, and there's no way possible then to make the whole thing 0. So we'll just work with the negative 3 and 3 as the only numbers on our number line. Remember, we noted that the numerator is always going to be positive. The first term always has to be positive, because when you square something, it'll be a positive number. And then the 18 is positive, so the numerator really isn't going to affect our sign at all. In the denominator, if we take something like negative 10, plug it in for the x squared in the denominator, it will give us 100 minus 9, which is positive, and a positive cubed is a positive. If we put something in like 0, 0 squared is 0, minus 9 is a negative cubed is a negative. And when we do 3, we could put it in like positive 10, squared it's 100, minus 9 is a positive. When you cube a positive, it's a positive. This tells us that we'll be concave up from negative infinity to negative 3, the union of that with 3 to infinity. And we will be concave down from negative 3 to 3. Now, although it changes from either concave up to concave down or concave down to concave up at negative 3 and 3, there are no actual points there because that's where it's undefined. So we will not have inflection points at those spots. We'll now use all of this information to sketch the graph. Now, because negative 3 and 3, it won't be defined there, we will have asymptotes there. So we'll want to be sure to draw those in. We had a max at 0, negative 1/9. And we'll now draw in our concave down and concave up sections. Now, something you learned that can help you sketch this graph, and we'll use it a little bit later in the unit as well, is if you have a rational function, which we have in this case, rational function just means it's a fraction, essentially. We can find where the horizontal asymptotes will be. When we plug in really huge numbers into this, both positive and negative in our original, because it's squaring, they'll both end up as, in the denominator, as really large positive numbers minus 9. Well, 1 over a really large positive number is a really, really small positive number. So both to the left and to the right, our horizontal asymptote should be approaching positive 0. So how that helps us is our concave up sections, that means will be above the x-axis. Then we've got a concave down section where we've got a maximum we've got to make sure we hit. And then we've got another concave up section, and as we had said, that should approach 0. That's all for today's video. We'll see you next class period.